All right, welcome everyone to the Friends of the DAO Star Party for August 21st. My name's Aaron. I'm going to be your MC slash host for the evening. We've got a great lineup for tonight. We'll be hearing What's Up in the Sky from Don Moffat. We'll have a great main talk on astrophotography, interpreting the universe, with a panel of EAA astronomers, electronically assisted astronomy folks from the Friends of the DAO and the Royal Astronomical Society of Canada. Following that, a little bit of astronomy news, and then Ask an Astronomer with James DiFrancesco, the director of the NRC Dominion Astrophysical Observatory on the hill we're sitting on tonight, as well as Jonathan Bernallo, one of our student astronomers from UVic. And then following that, we'll be getting some more images from the EAA crew, as well as, weather permitting, some images from the Plaskett as well. We're sitting on looking at the wind right now. If it gets too high, we may not be able to do it, but we're crossing our fingers. Before we go further, I'd like to take a moment to acknowledge that we are on the traditional territories of the Coast Salish and the Kwanghan-speaking peoples, who are the custodians of these lands and waters. This area has long been the gathering place of the Songhees, Esquimalt, and Saanich nations, long before the arrivals of the Europeans. We are grateful to have the opportunity to live, work, collaborate, and learn here, and we respect the continued connections with the past, present, and future in the ongoing relationships with Indigenous and other peoples within the British Columbia community. We invite all attendees tonight to reflect on the relationships you have to the communities that inhabit this land and share the night sky in wonder. If you're watching us on YouTube tonight, please give us a like and subscribe. That really helps us reach more folks. As well, you can follow us on pretty much all the social medias with the tag @FriendsDAO. That's @FriendsDAO. You can find us pretty much anywhere. As well, we are getting ready to open up. Still waiting on NRC to give us the official go-ahead, but we're starting to ramp up some projects, getting things tidied and get some new exhibits put together for welcoming the public back. If you'd like to become involved or help support our work, you can become a member of the Friends of the DAO or give a donation at centeroftheuniverse.org under the memberships or donations tab. Or if you'd like to get your hands dirty, you can go to the volunteer tab there and let us know what you can help us out with. And finally, before we jump over to Dawn, throughout the evening, if you have any questions about life, the universe, everything, what I had for lunch, although probably not that one, you can toss those into the either YouTube or Zoom chat. And those will go either to our presenters, or if it's a longer, more involved question, we may hold it for our Ask an Astronomer segment. And the questions don't necessarily have to be on the topic of any of the talks. For Ask an Astronomer, we can go pretty much as wide-ranging as you have questions for. So please be sure to toss those in. And I believe that's everything I have to say for now. So let's head over to Don Moffat for What's Up in the Sky. Hi, Don.
Hi, everybody, and welcome tonight. I hope you're all doing well. And what I'd like to do is tell you a little bit about what's happening in the sky tonight, and maybe a little bit about the full moon that's going to be tomorrow morning. So just for basics, sunset is at 8:16 tonight with full darkness from 10:16 to 4:14 a.m. And sunrise is at 6:18 a.m. And by September 4th, 2 weeks from now, sunset will be 7:48 p.m. and sunrise 6:35 a.m. So it's starting to get darker quite a bit earlier now, before 8 o'clock in a couple of weeks. So just like to show you what's here. You can see that that Venus is just actually hiding behind the trees here at about 8:45 in the evening. But you'll need an unobstructed horizon. So you can see this tree is in the way, and so it doesn't quite do it for us here. And after if you're actually probably the best thing to do is to go down to the water, someplace like the breakwater, and to have a look there. So someplace where the horizon, where mountains and so on are in the distance. So if you're having trouble identifying Jupiter, tonight would be a good night to have a look, because Jupiter is actually quite close to the moon. It's above and to the left of the moon in the sky, and you can see that Saturn is above and to the right of both of them. And full moon is tomorrow morning, just after 5 a.m., meaning it'll be harder to see the Milky Way tonight. And if you want to see the Milky Way, it's best to wait a week until the moon is out of the evening sky. And this is called the blue moon, this particular full moon, but it won't actually look blue. So what does that mean? Is it a sad moon? Is it a cold moon? And it's actually kind of a strange term. It used to be said that the blue moon was the second full moon in a month, but that's actually not true. It was actually Sky and Telescope magazine that got that rumor going some time ago. But they've corrected themselves, and they point out that it was actually the third full moon in a season. So in a season that actually has 4 full moons. And so this is the third full moon in the summer season. There'll be another full moon in the summer season. And the name actually originated in the Maine Farmer's Almanac. And it was termed blue so that it would not interfere with the other names for the moon, such as the snow moon in February, or June's strawberry moon, or the harvest moon. And as to why they picked blue, I still don't have any idea. It's a term that came from the 19th century and maybe lost to history. But you might ask, how often does this happen? And it happens about every 2 years and 8 months. And that's a pretty long time. And I think it justifies the term once in a blue moon. But you may have actually noticed lately that the moon has looked reddish due to the smoke thrown up by forest fires. And the finer smoke particles are similar in size to interstellar dust created by old stars. And although some are actually larger. And the smoke actually dims the light as well, as you noticed, and there's less blue light that makes it through the dust. And that's because the smoke particles are similar in size to the blue light and interferes. So you can actually see this effect if you look at astronomical photos. And I'll hopefully show this on the screen. And Calvin, if you can give me a nod just to let me know if this is showing on the screen.
Looks like it's showing, yep.
That's great. So this is actually a dust cloud in the Milky Way. And if you look carefully through the edges, you can actually see that, in fact, the stars are reddened. And so this is what's happening here is that the dust is about the same size as the wavelength of red light, about 0.7 microns. And so it just scatters very efficiently at that size. And this kind of thing actually happens with other types of fires as well. There's a fire with a muskeg in Alberta in 1950, but in that case, it actually turned the light blue, and that's because the droplets that came up were actually about the size of the red light, and it scattered out that component, and so it was really just the blue light that got through. And so this dimming and reddening effects of interstellar dust are very important in astronomy because they can affect how distances are calibrated, for example. And the DAO actually helped map the distribution of interstellar dust back in the 1960s, which was a very influential piece of research. And so when the moon gets out of the sky in about a week, you can see gaps in the Milky Way caused by interstellar dust that are blocking our view. So I encourage you to go look for that. So that's about it for me tonight. And I hope everybody gets out there and enjoys the nearly full moon.
Excellent. Thank you, Don. All right, next up, we have our main event, Astrophotography, Interpreting the Universe. This panel is going to be led by David Lee, who's an active member of the Friends of the DAO and the Royal Astronomical Society. He does a lot of fantastic work with astrophotography. He's done a lot of What's Up in the Sky segments as well, done some talks on doing your own astrophotography. So I welcome him, and David, do you want to introduce the rest of the panel?
Yeah, okay. I'm just going to share my screen first. Okay, I think I'll just start this and then I'll just introduce the people as they come in.
Sounds good.
So here we go. So welcome everybody. This was a request that was made like I think about the beginning of the year. I wasn't quite sure what I was going to do with this episode, but partway through I decided that I would make this a community event. So I have actually invited a panel of local astrophotographers. Many of you will probably know these people. We have quite a large Zenfolio site with not only these photographers, but others as well from the local community. I think it's an amazing display of the diversity of astrophotography here in Victoria. And I'll sort of tell you a little bit about some of the things that allow us to do this kind of magic, I guess. I've often described astrophotography as extreme photography because it's kind of like the hardest bits of everything. Like you've got vibration, you've got really high magnifications, you've got low light, everything that would make you unsuccessful. So anyways, I will introduce the panel now. There's Brock Johnson and Alec Lee, myself, John McDonald, Mike Nash, David Payne, Dan Posey, and Jonathan Rinaldo. And I'll tell you a little bit about them as I go through each one. But first, we'll go through the talk. So I thought about what motivates us. There's lots of different things. And everybody will have a slightly different story. And that's what I hope will happen tonight, that everybody will tell you their personal story. So for me, a lot of it is about seeing a different world. These are things that we don't see from our day-to-day life. When we walk outside and we walk down the sidewalk, we don't really see these vistas. Also, it's really important to me as a tourist of the night sky, capturing memories, just having something help me remember some of these events. The other thing is the feeling of discovery. I think most of the photographers tonight will tell you that what is so fascinating about this pastime is they get to see new things that they didn't even know existed. And we have lots of lively discussions on EAA about this exact thing. And then the other thing is citizen science. I think what's happening now is there are a lot of science agencies that are kind of opening up their data now to allow citizens to sort of help them with some of the research. A good example of that is the AAVSO, and I'll talk a little bit about that a little bit later. So early astrophotography, I thought this sequence was important to see how far we've come. So 14 years after the invention of photography, Henry Draper actually produced this image of the moon. So we're going to see some amazing lunar photography tonight, but this is one of the first. Also, the other thing that was popular were these transient events, for instance, the solar eclipse image that was done in 1851. So the Lick Observatory is a very famous observatory, and you can see the glass plate spectrograms to the left there, and also this image by E.E. Barnard. Now, I sort of invite you to sort of Google that name if you want to see some of the really early views of the universe. And this is at a time when they didn't even know about galaxies. They were called nebula at the time. So instead of the Andromeda galaxy, you hear them talking about the Andromeda Nebula. Also, things that happened in photography was also the discovery of the planet Pluto. So when you see astrophotography being used, it's often used to sort of capture an understanding of the time domain. Like over time, you see motion, right? And planets move, and that's how they discovered Pluto. Here's some images of the planet Mars from Mount Wilson in 1956. So we're moving fairly rapidly through the timeline now. but you get a sense for what they were capable of doing. And this is from Mount Wilson. You're going to see some amazing images from present day by amateurs or amateur. The thing that I remember most this afternoon when I was sort of digging through some of the archives, my own archives, I was wondering, well, what was happening in the 1990s with astrophotography? And the thing you'll see here, this magazine cover that I'm pointing to right now, this is actually one of the first CCD images. This is the Dumbbell Nebula. And this was actually published, I think at the time, Richard Berry was the editor of Astronomy magazine. And he also produced this do-it-yourself CCD camera cookbook. So before the days of commercially available specialty sensors, there was this chip, and I think it was a 245 or something like that, or 254 chip, and it was a very tiny chip. I think it was only like 240 by 240 pixels. It's very, very small by today's standards. But people were building their own cameras, and this worked okay for really small objects. But it was just the beginning, and this is in the 1990s. So today, well, what has happened today? So digital photography in the early 2000s really has made what we have today in astrophotography possible. I remember one of the first digital cameras that I purchased was a Fuji S2 back in 2003. And at that time, it was only 12 megapixels, which is kind of meager. And it was really only a 6 megapixel camera in actual fact. But it was built on an Nikon body, and I was able to use all my lenses. So many, many decades after that time, we now have quite a proliferation of camera bodies that are quite capable of astrophotography, and even specialized ones like this Canon 60D, which is old now. I think there's a new mirrorless version of that now. The other thing that's happened is we have small trackers now. So one of the things that we have to be able to do is follow the objects in the night sky because there's this apparent motion that has to be compensated for. So those trackers have gotten quite small. There's a proliferation of commercially available specialty cameras now. So not only CCD, but also CMOS as well. And those sensors are starting to flood the market now, and at, I would say, fairly reasonably prices. They're still not cheap, but still attainable. So what are the challenges of human vision? We only see in the visual spectrum, for one. So in other words, a lot of the images that we see are not just taken in the visual spectrum. In low light, we only see in monochrome, which is interesting. We don't see the colors that we see during the day because the light is not high enough level. And the other thing is that we can't really accumulate light. So in other words, if you had something really, really dim, your eye and brain can't sort of integrate that together and show a brighter image than is possible at one given instance in time. So what are the challenges of the environment? Well, to the left-hand side, celestial motion is a natural thing. Cosmic rays and the turbulence of the atmosphere. We live at the bottom of a swimming pool, basically. So it is difficult to get images of great clarity because of that. The stuff on the right-hand side, like in this area here, are things that we're probably in control of. Things like light pollution, things like artificial satellites that are being put up in the night sky. These are not the natural things that came with the universe. So how do you compensate for these things? So the whole discipline of astrophotography has a number of techniques to sort of overcome some of these challenges. And I like to show this picture because the relatively easy stuff is on this side of this border of 30 seconds. And the reason why I say that is some things can be handheld, like these nightscape pictures, like the setting moon, for instance. These solar pictures probably still want to be done on a tripod, but don't necessarily have to be. The lunar eclipse is the same. This halo can be just done with a very fast exposure. Now, I put the tripod here because this is an aid. Once you get past around probably about a 30th or a 60th of a second, you probably want to put your camera on a stationary tripod. And if you have a wide-angle lens, you're actually capable of taking pictures like these, up to about 30 seconds. And the reason 30 seconds is as long as the focal length of the lens is not extremely long, like a long telephoto or a telescope, you're not going to see any star trailing, which is part of the celestial motion. Now, if you want to surpass that, you cross the 30-second boundary, you're into tracking. So there are these portable trackers that are available now, and then telescope mounts as traditionally available. So the other technique that we're using is called, I call it tracking and stacking. So the tracking comes about from the mounts, the tracking mounts that we use, or the telescope mounts. And this concept of stacking is quite interesting. Remember I said that we can't, as humans, accumulate light. Well, by stacking, by using a computer, we can actually stack images or integrate images and get the effect of having more light. So you can see this image here. This is an example of a single frame that may have been taken that's tracked. And you see there's a bit of noise here. Over time, if you take a number of these images and you stack them together with a computer, with a piece of integrating software, you get a smoothing effect. And the reason for that is that noise in sensors is randomly distributed. So if you take images which have random noise in them, if you stack them, the signal of the image comes through, it rises above the random noise, because the random noise won't be in the same spot each time. So over time, and we could be using up to like 50 images, once you stack them, you could get a very smooth looking image like this. So this technique takes care of the celestial motion, as I mentioned, by tracking. And it also allows for the accumulation of light. And the other thing I didn't mention was you can throw away images too. So astrophotographers often cheat. They don't use all their images, so they just take the best ones. So there's a couple of specialized techniques that we're going to be talking about tonight. One of them is a video technique called lucky imaging. So we're going to see a demonstration of that with planetary imaging and lunar imaging. And then the other part is, how do we deal with light pollution? Well, there are filters that we can use to do that. Not only filters that are designed for lights, but also just narrowband, like very specific wavelengths of light. So lucky imaging, these are two examples. We're going to hear from these two photographers tonight. This is a technique where there's a continuous stream of images that are captured. And then what happens is those stream of images are culled, where only the best images are kept. And then they're actually run through processing algorithms that also enhance the structure and the edge details. So we're going to hear from John and Mike tonight about this technique. So the other thing, the other deep sky photographers here, something that is very popular now to sort of take care of some of these problems is something called narrowband and light pollution filter imaging. And the best way to describe this is the light spectrum that we have. There's a visual spectrum, and then there are these areas where there are specific wavelengths like O3, hydrogen alpha, and silicon. And those types of narrowband filters, they are deployed to isolate a particular wavelength. So there are actually many celestial objects which have a high concentration of hydrogen alpha, and it actually helps to sort of isolate that wavelength to see the detail. Also, it diminishes any light pollution that might exist as well, because that doesn't pass through. The other thing that emerged was this generic or general light pollution filter as well. And these are meant to notch out, and this is an expression we use, the light that comes from artificial lights. So for instance, the high pressure sodium lamps, which are orange, they are notched out by the filter. In other words, they pass everything except. So except for the orange filters. And there is a filter now that's available that also accommodates some of the LED lighting that we're switching over to as well. So the other thing before we get the panel, I just wanted to let you know, don't fear if you don't want the cost or can afford the cost of some of this equipment, there are data services that are available, and some of them are free and some of them are pay. For instance, the organization that I belong to, the Royal Astronomical Society, we have a robotic telescope that is part of our society. And often there are projects, for instance, right now, I'm attending a course on exoplanet transits. And that's being done with a robotic scope that we have down in California. NASA often has like free astrophoto challenges. So they just have free data that is out there. So you can put those together. And then SLU is an American company that has telescopes in both the Canary Islands and also in Chile. So I actually belong to SLU as well, because that allows me to image objects that are in the southern hemisphere that I can't get to. By the way, you don't have to buy expensive license software either. There's plenty of open source to process data. And then the very last thing I'll mention, I've already mentioned the exoplanet exploration. A lot of these astrophotography skills are directly transferable to things like variable star observation and exoplanet discovery. So you can do your bit in terms of citizen science as well. If the pretty pictures aren't enough for you, you can get a little dose of science as well. Okay, so I think at this point, I think I'm going to start maybe introducing some of the panel. You've heard a little bit about some of the challenges. You've also heard about some of the techniques. Now we're going to make that really real. I'm going to start with Alec Lee. Alec and I actually met on, I believe, on the top of Mount Ptolemy. Correct me if I'm wrong, Alec. In the dark, we were waiting for the comet. We were waiting for Comet Neowise, and that was such a magical morning because I remember the noctilucent clouds that were emerging as dawn was coming.
Yeah, absolutely.
Why don't you take it away, Alec? I think you have a picture of that, in fact.
I do. Well, I'm going to actually start. Now I need to get into share here.
Yeah, I'm going to stop.
Okay, there we go. Yeah. Great. And share. I can start with this one. And let me just get into my slideshow. So we may as well start with this one. And this is where you and I met. I guess it was about 3 o'clock one morning. On
it was
Mount
somewhere between 2:45
yeah.
and 2:50.
Well, this shot was taken at 3:58, I think.
Well, there you
go. And we had been taking lots of images. But what really blew us away was to have these noctilucent clouds, as well as, of course, Comet Neowise here. And for me, this is just so illustrative of why I'm doing this. You mentioned that feeling of discovery, and that's been with me since I was a kid. I think since Boy Scouts, actually. You know, I first went out in the woods and was shown the night sky and the Milky Way. And then to capture memories, because I've had an interest in photography as well. So to combine those has been great. And then to have a visitor like Comet Neowise here was just the icing on the cake. So my wife rolled over and I got up and drove over to the top of Mount Ptolemy, and that's where we met, David. This particular image was taken with my APS DSLR. It was a Nikon 500 on a tripod, a wide angle lens. I used a 24 millimeter f7.1 ISO 1000 and a 3-second exposure. This was about an hour and a half before sunrise. And what just blew me away was the brightness here. And these noctilucent clouds being so high reflected, the ice crystals reflected the sun as it was just gradually moving up towards the horizon. I just used a manual focus, which is always a challenge doing this. And I will explain in the next series of images how I did that, and just auto white balance and so on. And then I processed this image in Photoshop. I think the point that really stands out here is that if you've got a decent camera and a tripod, you can be doing this, and it's quite manageable. So this was a real treat. And then I followed Neowise for the whole month of July. This was early on when it was visible in the morning, and then of course it became more visible in the evening. The other image that I wanted to show you here is of the Milky Way. And again, this has just been a fascination for me. But one of the biggest challenges that I've had, and I think anybody who's trying to take a shot like this, is finding a place where there is no artificial light. So last September, we did a trip up to San Joseph Bay, just very near Cape Scott at the northwest tip of the island. Pitch black, it was a new moon, and it was just magic. There was hardly anybody there, which was quite amazing as well. So I set up here and just began to shoot. And here I used my full frame camera. It's a Nikon D810 with a very wide angle lens, 16 millimeter. And I exposed for 25 seconds. I really think I was stretching it, but as you can see, the star trails are not as visible here, but when I zoom in, they start to be. I used ISO 1600, f2.8 is the aperture opening, and of course I mounted on my tripod.
Actually,
real
just
treat.
Yeah,
Sure.
actually,
Yeah.
sorry. Actually, just for the viewers' benefit, I think what Alec's showing you is, remember I was talking about that 30-second barrier. As long as your lens is very wide, the trailing is not very apparent.
Exactly. Yeah. But as I say, if I zoom right in, you'll start to see it, but it wasn't apparent here. But what was a treat, of course, was having Jupiter right here and Saturn in the field of vision. And then, of course, this visitor, just a meteor streaking across the sky during that 25-second exposure. For me, the real challenge is getting a good focus. And what I found to be the best way is to use live view on my camera and pick a bright object like Vega was visible here as well. There's Jupiter. And so just to zoom in on that and then focus as best I can with the camera, and it seems to work out very well. The other thing that I'm trying to do with these kinds of images, especially something like the Milky Way, is to have an interesting foreground as well. And in this case, just the water in San Joseph Bay was particularly stunning. And so I just wanted to accent that. You can see the reflections here of Jupiter and the Milky Way itself in the water. It was a very magical time, and it certainly captured a big memory for me that has persisted. So yeah, I think that's pretty well it that I wanted to say, David, unless there are other things.
Oh, that's wonderful. Yeah, that's absolutely wonderful. Thank you so much, Alec.
Oh, my pleasure. My pleasure. Thank you.
As I mentioned, I do share a lot in what Alec does, because I was definitely a photographer first. I've been like a 50+ year photographer. So astrophotography came to me halfway through. But I always have the photographer's sensibility as opposed to just a straight astrophotographer. So
yes, I feel the same way.
Yeah, so I definitely have a love for that. So in actual fact, that's probably about the right time for me to jump in. I'm just going to share my screen. I think I'll start with this one first. So every picture, or often my pictures, have a little story behind them. Sometimes a sad story, actually, or a story of ill preparedness, let's say. So impulsively, back in 2012, I had never seen an annular solar eclipse before. Now, the annular eclipse is a little bit unusual in the sense that it doesn't fully cover the sun. So it leaves this round ring, and they call this the ring of fire. And it also has these kind of odd shaped horns as well during the process of the eclipse. Now, I impulsively bought a plane ticket to go to Cedar City, Utah for this. And I was just kind of debating, should I go, should I not go? So impulsively, I bought that ticket. So 3 days before, I was in a bit of a rush. And I was preparing. And in fact, I think one night before I went, I thought, I should practice. I should practice. They always say you should practice. So I went out and I practiced, and I thought, oh, there's one thing I can't quite do tonight. And I said, no worries. I've got a couple of days before the event. So I'll fix it. I'll test it later when I get down to Utah. So I arrive in Utah and I realize I haven't packed everything that I needed to. So in fact, I didn't pack the tube that I needed in order for me to use my camera to this eclipse. So I was in a bit of a tizzy now. So here I am. I go to the Home Depot and the Walmart there, trying to find something that I could fabricate to build this tube that I needed to put into my telescope. But I couldn't. So the story goes, or the story is, I took my point and shoot camera, which is quite an inferior camera to the camera I was going to use. And I ended up having to actually just point it down the barrel or down the eyepiece of the telescope. So these are what we call afocal images. And I had a hard time focusing it as well, because normally what you do with afocal is you set your camera for infinity. Well, this was an AF point and shoot, and I had the hardest time getting it to focus on infinity. So it took many tries. Good thing this eclipse took a long time. So I had enough time to get each of the phases of the eclipse. But that's my little story here. And I have I cherish this moment. When I was there, I was actually in a school ground with all these people, and I could hear the kids chanting ring of fire," as the thing came out and centered over the sun. So an amazing memory. So here's another image. I think this is Mars, actually, Mars and the moon. And here's another interesting fact. I actually don't like it when the sky is pristine. I always like to have a little bit of interest. So I was very happy when the clouds came by. Most people are not happy about clouds, but I was actually happy about the clouds that came by, because it created this beautiful lattice in front of the moon, along with Earthshine. And I remember waiting. I was there with two other astronomers. We were at King George Terrace, I think. And we had come down and it was totally socked in. And then I thought, well, is it going to come out? Well, I can't go home now. I driven all the way down here. So I basically just waited. And this is what happened. Eventually, the moon emerged along with Mars. And it is one of my favorite shots. So yeah, sometimes it isn't always bad when you see clouds. Okay, let me see, who's up next? I think it will be John. John, can you show us?
I can.
Yeah, show us your planetary shots.
Okay, can you see what looks like a
Yeah, I see your PowerPoint.
Okay, I will just start that. I'm going to talk to you about capturing planets with a camera. I've done astrophotography for quite a while, starting with film way back. And I've done it with, I've looked at almost all of the things in the sky that you can see. But recently I moved to the middle of the city where there's quite a bit of light pollution, and I decided I guess it's time to do planets. They're nice and bright, so the light pollution doesn't really bother me too much. And I'm having fun learning how to do planets now. I have a patio outside the apartment I live in, and this shows a Schmidt Cassegrain telescope that I use. And for those of you that have, whoops, I know it does that to me, just hold on. For those of you that have looked through a telescope, you won't be used to seeing all this gubbery on the back of it, but I'm just going to explain a little bit what it is, because if you don't know what that is, you won't know how we do this. So imaging planets, First of all, it takes a lot of magnification. So you need a telescope that can provide quite a bit of magnification, and then usually you supplement that magnification by adding a Barlow lens. In this case, it's called a power mate. It multiplies the magnification by a factor of 2.5 that the telescope already has, which can give you a pretty decent sized image of the very tiny sized planets that you normally see in a telescope. The other issue that we have to deal with is atmospheric distortion. David has mentioned the turbulence of the atmosphere. That results in an effect we call poor seeing. Astronomers refer to the bouncing around that a star or a planet will do as you're watching it as seeing. And the other problem is refraction, and we have to deal with both of those, and I'll describe them. Now, lucky imaging with high-speed cameras that David mentioned briefly is the way to deal with that poor seeing or turbulence in the atmosphere. And to do that, the easiest way to do that is to use a high-speed camera like this little camera here. It's quite small, it's relatively inexpensive, and it takes video at high speeds, up to 120 frames a second for planets. So that allows us to capture moments of good seeing and stack those images together. Now, to beat the refraction, there's a couple of things you can do. One thing is, if you use a color camera, you can separate the colors in Photoshop or some other program and realign the colors and put them back together. The reason you need to do that is because the atmosphere is acting like a prism for anything that's low in the sky. And planets are frequently low in the sky if you live in the northern hemisphere, as we do. So this device is a way of doing an even better job. It's called an atmospheric distortion corrector. And it has a couple of levers on it that operate two tiny prisms inside. And those two prisms can allow you to tune out the refraction that the atmosphere is producing and get a very sharp image. And so I use both of those things. Now for cameras, I'm not going to say much about this. Any camera will work to get a picture of a planet. But if you want a really good picture, using one of these video cameras is far and away the way to go. So let me just show you this. On the left, you'll see a video that I took in the process of getting a picture of Mars. And you can see it bouncing around. That's this atmospheric turbulence, which we call seeing. And this is a night when the seeing was actually not all that bad. Sometimes the seeing can be so bad that the planet will not even stay in the frame. It just jumps all over the place. Well, this particular video that I'm showing you is the same one that I used with software to pull out the best images that correlated together and then sharpen it to get the image that you see on the right, where you can see quite a bit of detail. There's a tiny bit of detail showing in the video, but a lot more detail showing in the processed image that you can see there. And then if I do that with all three colors, red, green, and blue, I can put together color images like these ones. Now, one thing to mention about Mars, if you want to get a picture of it, it comes close to the Earth every so often. And the last couple of times were in June 2016, and then the spring of it was the fall of 2020. And it's called opposition when that happens. And so these pictures were taken with a small refractor. These were taken with the one that I showed you earlier, a bigger mirror on this telescope made for a higher resolution, so I could get more resolution out of it. Now, I just want to show you one other thing, and that's Jupiter. Jupiter's a wonderful planet to get pictures of. First of all, it's fairly good size, bigger than other things in the solar system. And it has this beautiful red spot. That's a storm that's been going on that planet for as long as telescopes have been pointed at it. It's a big cyclonic storm. Now, in this particular set of pictures, I was trying to capture an event that happens every so often. The moons of Jupiter can make shadows on the planet. And once in a while, there'll be two moons that are making a pair of shadows. And that's what I captured here. This moon over here is called Ganymede. And there's a moon right here called Io. And Io's shadow is right here. Ganymede's shadow is right here. And here, a little bit later, the planet has rotated a bit. Ganymede has moved a bit, so has Io. And here Io has come out from in front of the planet, and Ganymede is a little further away. And again, you can see the two shadows that they make. And I just want to show you what that looks like. I took a number of images of this kind and turned it into a video. It goes by kind of quickly, but you can see it happening here. I'll just maybe run that one more time so you get a better chance to have a look at it. And that's basically what I wanted to show you about imaging planets. So I will stop my sharing and you guys can carry on.
Well, thank you very much, John. I'm always amazed by your planetary work. And by the way, John isn't just good at planetary stuff. He has a whole huge gallery on Zenfolio that you should check out. Anyways, somebody else who's actually using Lucky Imaging as well. Where are you, Mike?
Right here.
Hey, Mike.
How are you?
Good.
Yes. Lucky Imaging has been the key to unlocking a lot more detail in what I've been able to capture, that's for sure. Yeah, I like yourself and others, I've come into this through photography. I've been a photographer my whole life, and amateur, of course. And it started by one day just deciding to put my camera and birding lens. I used to take a lot of pictures of birds. And I stuck it on a tripod and pointed it at the moon. And I was absolutely astonished at the result. I had seen lots of tremendous moon pictures before on the internet, of course, but I had no idea that I could capture anything like that. And it swiftly progressed to a near obsession where lunar photography has taken a bigger place in my life than other types of photography. So now I started with a camera and a tripod, and now I'm using astro equipment, and I'm still refining, what I do, and maximizing what's possible here on Vancouver Island, at least with what we have in the way of seeing.
Mike,
yes.
Mike, could you share some of your images with us?
Yeah, you bet. Okay, so here's.
You'll have to share your screen, Mike.
Yes. Okay. Great. All right. There.
There we go.
So this
Excellent.
is a shot that my most recent one that I've done, and I did this just from my front deck actually, and you can see I'm set up here with it. That's my bigger telescope that I use for close work, but the photo that I'm going to show here was taken with this one, which is a fairly small, most people consider this a small telescope. It's 4 inches in aperture. And you can see that I've got a planetary camera there attached. And that's actually what it's capturing right there. And it's this video file that's running. This is just obviously a snap of it while it's working, is what I made my image with. And here you can see an example of, this is an actual unprocessed frame from the video.
That's a single frame?
That is a single frame straight out of camera, basically. And as you can see, it's pretty, there's still a fair bit of detail. It's dark, but it's, you know, it's not super sharp. And then when I'm done, well, I take it before I move to the finished one. I'll just show you. This is what. No. Oh, I'm sorry. I'm going to skip ahead to. This is the previous one, and this is the finished file here. So after I've let the camera take about, I think for this one I've said down here, I've took 2,000 frames. And then using very similar to, you know, the same techniques really as John, I run it through software that grabs the best of those frames. And in this case, it was 150 of the 2,000 that I took. This is a 20 megapixel camera, so it can't run as fast as the camera that John was using. I think I was running at about 20 or 15 frames per second or something like that.
But you have a wider field of view, though.
I have a wider field of view. Yeah, this is 20 megapixels. So, you know, a typical planetary camera might be about 2 megapixels or something like that. But if you zoom in here, you can see that I was able to capture quite a bit of detail. So that one is the first of the 2 images I wanted to show. That was with my smallest scope. This one here is I really intend it to be what they call a grab and go. It's just something that I can go to any sky with simpler equipment and look at the sky. Now my other one is right here. This is with a slightly larger telescope. It's 140 millimeters. And I'm set up in my driveway here. That's the beauty of doing planetary and lunar, but we don't have to go to dark sky. We can shoot it just about anywhere. And here again, I'm using, this is a bigger telescope. It's 140 millimeters, and my same camera, the way I've got this configured, that is what I'm capturing. That's the full. So I can't get the moon in one shot here. I'm making what they call a mosaic. And I took a video here of 2,000 frames, or I think, and I think I did this in four panels. And then here is something I wanted to show. This once you zoom, this is the actual capture, a little video clip. Now, if you look here, you can see I've got this zoomed in to 236%. So it's showing on the screen there at larger than pixel to pixel. But this is how I would focus on the moon in the first place. And here is actually a little clip going. So it may look actually really shaky, but to tell you the truth, this was great seeing. This is pretty steady.
So I guess when you say that, Mike, it's probably a smooth undulating movement, not a jerky movement. Maybe
yes,
that's why you say that, right?
Yeah, yes. And the important thing with Lucky imaging, if you're looking at it while it's shooting, if you can see the sharp bits, if you can see sharp moments, just the flashes of them, then you have a chance at a very good final image, because those are the ones you're going to keep.
Right, because the software gets rid of all the fuzzy stuff.
That's right. So now I'll just backtrack for a second and you can see what was on the camera. I will show you a single frame of that particular capture, which is right here. Now this again is just a single unprocessed frame. Now, when I first started with all this, I would have been thrilled to have that as my final result. But now, what I do once I've taken the, all the pieces of my mosaic and I put them together, then I end up with my final image that once I've put everything all together. And here you can see what that has been transformed into.
Yeah, you've got much better edge detail now.
Well,
Yeah.
This is what I really, this is what I love. There's many different ways to process, and the end result of what I do, I really want it to look like you're flying over the moon. Like, you can actually process. I could take this same data and do it in such a way that you can see more details. And that's a completely valid way of doing things, but that's not what I go for, really. The detail is part of it, but I want it to look like the best photograph that I could take,
Right. So you don't want to overdo it.
Well, yeah, overdoing, but yes, I don't want it too much. The one other thing I'd love to show you is I'm going to throw this in if I have a minute or two still.
Yep.
This is one of the softwares that I use to process a stacked image. That's when your software has stacked only the best files, and now you have a stacked image and you need to sharpen it. So here is not one of those two images, just one that I grabbed out of my computer. This is a stacked image that's ready to be sharpened and processed. This program here is called IMPPG, and it's actually a solar processing program, but it's just equally good at the moon as long as you're only doing black and white.
Were you intending to show that to us, Mike? Because I don't see your software. You must be on a different panel.
Oh no, I have to. Yeah, I thought I was sharing this, and I guess I'm not. Okay, yeah, I better. Sorry about that. I think maybe I better let that go because I don't know how to get to that, how to share that.
Well,
screen.
you can. Why don't you just let us know in chat what it is, and then we can look it up ourselves.
Okay, yeah, I will do that.
Okay, thank you so much, Mike. I'm almost so impressed by your lunar pictures, and I know Randy is as well as a sketcher. He always loves to compare his sketches to your images.
Thank you very much.
Yeah, thank you.
It's been wonderful.
Mike, can you release your screen? Okay. Oh, there we go. Good, thank you. I guess Jonathan is up next. Jonathan is one of our students that is from UVic, and he's been helping us narrate this summer, but he's an astrophotographer in his own right. Take it away.
All right, thank you very much. So, all right, can you all see that?
Yes.
All right, so first image that I have planned to share tonight is this image that I just took recently, actually, in the past month or so, of the Eagle Nebula. And this is moving away a bit from some of the previous images that we've seen, in that we've seen nightscape images, and we've seen planetary and moon images, which are done by compiling frames from the video. This one is sort of at the extreme end of what people think of astrophotography, in that it's a stack of very long exposures taken through narrowband filters with a monochrome camera. So the telescope that I was using for this shot is a Org 101 ED refractor. So it's a 4-inch refractor with a focal length of about 640 millimeters. And I shot it in the Hubble Palette. So basically, all the red you see in the image is indicative of the presence of ionized sulfur in the region. All the green tells you that there is hydrogen there, and the blue signifies oxygen.
Yeah, so this is not a traditional palette, is it, Jonathan? Normally when we see H alpha, we think of magenta or kind of a reddy color.
That's right. If you were seeing these wavelengths with your own eyes, both sulfur and hydrogen will look red, which obviously presents a problem when you're trying to combine these sets of data in a way that is meaningful when you look at the final product, because it sort of defeats the purpose of using two separate images, two separate filters.
Yeah, the idea is to sort of separate the features.
That's right. Yeah, you want the color to convey information rather than just beyond just the general structure of the nebula itself. And in this case, we want to know what the structure is made of, what molecules are building up this nebulosity. And the Hubble palette is, it's a false color palette, but it is quite commonly used by astrophotographers to map each of their filters to a different color. So quite often you'll see pictures on the internet of people who image mostly nebulae, and if you see sort of that pale blue and dull brown in those images, that's a good sign that they're imaged in the Hubble palette.
Very nice.
I think that's all I have to say about that image. And the other image that I have prepared is a sort of a step in the opposite direction. This was, I took this one during the January 2018, I believe it was, Lunar Eclipse. And I was using the same scope, but a different camera. I was using, in the previous image, I was using a ZWO 1600 mm, which is a cooled monochrome camera. So it's cooled it has a Peltier cooler basically attached to the back of it to cool down the sensor to reduce the noise in the image. But this one was just with my Canon Rebel DSLR. And it's just a single exposure. There's no fancy video stacking or anything like that going on. The exposure itself is a few seconds long, I believe. So I was basically taking a lot of single exposures, and I started off with short exposures. But then I sort of thought, well, I've taken a bunch of single exposures, so I might as well see how long I can go and see what upping the exposure time does to these images. And actually,
you can also see the stars in the back. You also see the stars in the background too. Yeah.
Exactly. Yeah. That was another benefit to upping the exposure time a little bit.
Yeah, they're always different. Like a lot of people think, oh, you photograph one lunar eclipse, you photograph them all, but they're all a little bit different. In fact, I even have one that is one of my favorites, and it has a teal color. And I thought that was an artifact or something was wrong, but I found out later it has to do with the ozone. So it's actually real. It's a real thing. Yeah. Wonderful. Yeah. Thanks, Jonathan.
Absolutely, yeah.
I think we have David Payne up next. Yeah, David.
Hi.
Speak to us.
I'm speaking. So I'm going to start out with, I'm going to be talking about deep sky images. That's just the slant I take to my astrophotography. But I'm going to start out with a couple of deep sky images. This is one of the most photographed images in the night sky. It's the B33 Horsehead Nebula. It's again taken with narrowband filters, as Jonathan has said. The reason the reason I included it is it's part of an actual very nice vista, which is only part of a big nebular complex where stars are born. That's called the Orion molecular complex. And of course, this is in the constellation Orion. And this is a very famous vista. And I'm showing this for a couple of reasons. There's three kinds of nebulosity out there. And I take pictures because I like exploring space through photography. I'm not a photographer as such, so what you see is what I've learned. Not that this is a particular grand picture of this vista, but I do think it does capture enough of its beauty. It has three kinds of nebulosity in it. What you see outlining the backdrop of the Horsehead and the Flame Nebula there are actually gases, particularly hydrogen, absorbing radiation from the stars around it and then re-emitting light in its characteristic wavelengths. And that's forming the bright parts. And then you've got other parts of dark nebula, which are generally molecules or heavier ions, or particularly thick hydrogen, where it's actually blocking the light from passing through it. So what you see is basically a negative space, and this negative space in this picture, I guess, outlines sort of a horse head, hence the name. And over here you can see it looks like a giant flame going off, and hence the name of that nebula. There's also reflection nebula, where the gases or material or dust doesn't re-emit light, it just reflects light that's shining on it. And you can see that kind of nebula around a central star here that's showing up in blue. Now, while the vista is particularly nice, I didn't pick this one because this is a particularly great shot. It's not a bad shot, but it's not a particularly great shot of the vista. The reason I picked it is also because it has a bit of a special meaning to me and a bit of historical meaning. When I was a child, I was a young child in the middle of the Apollo mission era. And back then, everything was labeled space age as the marketing ploy. So you would get a space age toaster if you wanted to. And what I happened to get was a Rand McNally Space Age Atlas. And it was published in 1964. I'm not sure I've got it brand new, but I'm sure up in the upper right-hand corner of this image is a picture taken in and about 1964, maybe a little bit before 1964, of that Horsehead Nebula. And this image was taken using a 200-meter, someone's dinging me for some reason, taken by a 200-inch, which was 200-inch telescope, the Hale telescope in Mount Palomar, which is owned by Caltech. And it was state-of-the-art kind of picture at the time. Now, what I'm thinking is that this picture, the picture that I took, I've taken the Horsehead and just blown it up to about the same scale. You can see the stars are basically in the same places. But I would venture forth that my picture is better than that picture. So while I was a child wondering at what is this object, I can't believe something like that exists, let alone what created it. And looking at this picture below, I would never imagine that I'd be taking a picture of this object myself. So I just want to take a couple of minutes and talk about, well, how can I take this picture myself? I don't have a 200-inch telescope. In fact, I'll give you a view of the telescope that actually took. So this is the telescope that actually took that. It's only a 5-inch. It's not 200-inch. So why can I take that? Well, there's two main reasons. One we've touched upon already is the camera. So you can imagine back in 1964, they only had film cameras. Now, today we have CMOS and CCD digital cameras. And there's a whole bunch of advantages that a digital camera brings. One is that you get an instant feedback of your picture. There's no processing. And probably another major one is the cost. So each time you take a picture, it would cost you the film with a film camera, it would cost you the film or the plate, and it would also have another cost of actually processing that plate. So your cost per picture taken would be astronomical, if you pardon the pun. It would be very limiting to only necessity. Now with digital cameras, we can play around. We don't have to go to a dark room to develop it. AP astrophotography was also restricted pretty much to black and white because what you needed is to have more sensitive film, and color would be both even more expensive and probably less sensitive to light than we could get with black and white. And last of all, point out that many of our images today are created by stacking a number of images together to remove the noise and enhance the signal. And that's very easy to do digitally, but it's either difficult, extremely difficult, if not impossible to do with film. So that picture was really brought to you mainly by the camera, but also I want to talk a little bit about computing too. So microchips weren't around back then. You'd be lucky if you could brag that your radio had 9 transistors in it, while a microchip might have thousands and thousands of transistors in it. So computing is the other big difference. So when that black and white picture was taken with the big telescope, you would have had someone at the controls of the telescope looking through a second telescope. And if you can imagine, I've got a second little telescope on top of my imaging telescope. So you'd have someone looking at that, pointing at a star, making fine adjustments all night to make sure that the big telescope didn't vary off and blur the image that you were going to capture on your film. So that was the process. Now what I do in my backyard is I stick a little camera in this, hook it up to a computer, and the computer makes those fine adjustments for me. So I can go to bed actually and go to sleep. And the telescope itself, the computer will take over for me and make sure these fine adjustments are made. So even on taking the pictures itself, I can program a series of pictures. I want more than one image, so I can stack. The computer can control all that. The computer can judge the images. They can do focusing for me as focus needs change over the night. And all those things on the image capture side, but also computers. And I just got another image I just want to show here of the actual computer running this. It's a very small mini computer, it's called a NUC mini computer, and it just sits at the mount and runs everything. Just below, it's got some USB cables that talk to the camera and the mount, and some Ethernet cables that talk to the mount, and all I do is program it. I can look at what's going on by either remoting into this little computer with a tablet or a laptop, or I can even look at what's going on in it from my desk inside my house, especially nice on a very chilly night. But the other bit of the magic comes in with processing on the inside. So we stack the images, as we've talked about already. We sharpen the images, we denoise the images, we try and bring out details in the images with either programs called PixInsight or Photoshop, and to do all that. So at the end of the day, we no longer need a 200-inch telescope and have to be satisfied with black and white image. We can actually do better even in our own backyards today. Now, just to give you an idea, sense of how that technology has changed and the time scale, this object was first cataloged and identified in 1913. And if you can imagine, this black and white image was taken 50 years from it first being identified. So that's where technology took from identifying it and maybe drawing it and describing it. 50 years later, they were actually taking images from that. 50 years later, we're taking images in our backyard. It's now 50 years later since this image was taken. 50 years later, we're now taking images from our own backyards if we like. So I think I've dwelled on this one enough. Do I still have time to show another image?
Just quickly, Dave, if you could.
Okay. The second image is another image taken this time with a larger telescope on the same mount and the same computer controlling it, but it's a much zoomed in image. And this is of a nebula called the Cave Nebula. It's categorized sharpless 2-277 or (155). Anyways, it's not that important. And this is showing an area of great, I didn't use the Hubble Palette on this. So what you see here is a bunch of red, now indicating hydrogen, which is a more true color of the hydrogen primary spectrum emission. So to an eye, it would appear reddish if you could get such a view from outer space. And I've assigned sulfur to a yellowish color or a greenish color, actually, which kind of turns the whole image yellow where there's a lot of sulfur. And oxygen I've assigned to blue. There's not a blue in there. But it's another good example of where there's reflection nebula, emission nebula, and dark nebula. And if you remember at the beginning, you saw that dark nebula was actually blotting out part of the Milky Way. And you can see in this image, it's actually blotting out the stars behind it, or even nebulosity that's behind it. The red images are, again, hydrogen, which is actually forming stars. And these two types of nebula actually have to work in concert to create new stars. what you have to allow is gravity to pull all that hydrogen in together into a small space so that it can ignite as a star. But you got to block the stellar winds from all these stars around from blowing it apart before it can form a star. And that's where the dark nebula comes in and shields that star forming area. But you can see the results of the waves and all the various patterns and shock fronts and all sorts of flow processes that are taking place out in outer space, being pushed around.
So Dave, hold that thought. We've got to move on to other people, but we're going to continue the discussion when we hit EAA at 10.
Yeah, sorry about that.
Yeah, no problem. Thank you.
Thank you.
Brock, I think you're up next.
Hello.
Hey, Brock.
How's everybody?
Good.
I guess I thought I'd start just by talking about sort of where I started out with astrophotography. So let me share my screen here. Can you guys see a picture of an old Dobsonian?
Yeah.
Yes. So this is probably one of the first times I did astrophotography was back in, I think it was 2012. There was a transit of Venus. And I just pointed my Dobsonian up at the sun and projected it onto a piece of paper and then basically took a picture of the projection on the paper and got a picture of the transit of Venus.
It's amazing how big it is.
Yeah, the eyepiece did a pretty good job of blowing it up. I even got some sunspots.
No, I just think it's amazing how big Venus is, right?
Yeah, for sure.
You don't think of it as being very big.
Yeah. And then I sort of tried a little bit of stuff where I'd mount my DSLR to my Dob, and this was pretty useless for anything other than some really, really bad pictures of Jupiter. And so, I kind of tried it a few times over a few years, but kind of didn't go anywhere with it because it was mostly non-fruitful. And then last summer, I splurged and bought myself an actual telescope that had the ability to track the moving sky, or at least keep the moving sky in place as the Earth moved under it, and managed to actually start to get some reasonably good images. So it was a bit of a crash course, but I wanted to get a picture. I played around a bit in the fall, and then in the spring or late, I guess it was early spring, sometime in March, I started to get the Orion was up in the sky, and so I saw a lot of pictures of how great it looked, and I wanted to get a picture of it. So, and I also knew that the core of the Orion Nebula was extremely bright, so I took a number of shots at different exposure levels. I think I did 300 seconds and 180 seconds, and I even did some 10-second shots. And I guess this would have been 360-second ones here. And trying to actually get some of the really dim stuff and some of the really bright stuff. And you can see here, there's a whole bunch of images of each of the different exposures, which I used some stacking software to.
Yeah, there's quite a dynamic range between the trapezium and the web-like structure on the outside. It's huge.
Yeah, well, these images at the bottom were just, I think, 10 seconds. So for 10-second exposures, I was able to actually really well pick up the trapezium, but of course, nothing else, just this little blob in the middle. And then with a 180-second exposure, the trapezium was just gone, just a big white blob. And of course, 360 seconds, there was the trapezium and the entire area around it was just completely incinerated. So there was really no way to see it. So what I did is I composite it together in a bunch of different layers using layer masks and stuff. And it allowed me to basically get all of that dynamic range into one image. And this is the final result.
Yeah, this is kind of like an HDR image.
Yeah, it's kind of like an HDR. There's probably more automatic, elegant ways, but I was just kind of hacking around in some image editing software. But I did manage to get the trapezium, and I also managed to get a reasonable amount of, the sort of kind of cloudy material. I don't know what kind of dust or gas that is. But then, of course, there's a lot of the red nebulosity of hydrogen. And this was actually pretty happy with that shot, considering I didn't mention as well, this was just taken with a DSLR. Then I took the DSLR apart and removed the filter that knocks out all the red. So managed to make it much more sensitive. So I was able to actually get that shot. Was pretty happy with it.
Yeah,
I've done better
excellent.
since then, but it was kind of a big step for me because it was one of the more challenging ones involving, combining things. And
Yeah, I guess when you get to this level, there is a fair bit of planning and a fair bit of orchestration in terms of getting all the pieces together to combine.
mhm. Yeah, it was
Very nice.
over 2 nights and quite a few images. And then later on, actually, I ended up, doesn't look like much, but there's a bit of a story behind it. A very generous guy in the group lent me a monochrome camera with a filter wheel. So I took 3 pictures, this picture, and this picture of the North American Nebula, which don't look like much until you stretch them. But then you stretch them, and this is actually the view of the sulfur emissions in the North American Nebula, just through a narrowband filter. And this is the view of the oxygen in the North American Nebula. And there's also the Pelican Nebula up here. And then the hydrogen. And everyone can probably guess where this is going, but I was able to combine them together. And this is actually done in my best attempt to make it look as close to possible as the real colors. So I used hydrogen and sulfur in the red. I did actually change, I used a slightly different mix of red and green in order to just make it appear that the hydrogen was not the exact same red as the sulfur. A little bit, made the hydrogen a little bit shorter wavelength appearing than the sulfur, which is kind of the way it really is. And then I used the oxygen in sort of as close as I could to sort of a cyan, which is pretty much what you get around that 500 nanometer range, is a nice cyan color. So I combined those all, and I was really happy with this image because it has both really interesting texture around this area, which is, I think, called the wall,
Yeah.
the Cygnus wall. And
Yeah,
then,
that's my favorite part of the that area is the wall.
and then the Pelican Nebula. And there's actually a surprising amount of detail up there. I don't know if I can zoom in. Yes, I can. So you can actually see the some of the familiar details in that sort of region. And I was pretty addicted to how well this cooled camera was able to get rid of the noise, because the noise in my Orion Nebula was pretty atrocious, but I was able to get some really good images with this thing. So it was a lot of fun to play with.
Yeah, very nice,
And-
Ron.
And also it's funny, the dark nebulosity in here is really neat, because it kind of, at first glance, kind of looks like you're looking through to a dark background. In fact, what this really is dust that's actually more in the foreground, and it's blocking the light from behind. So it's just opaque, dark dust. But it's really interesting, the contrast in there. So, and I find it really, it's a beautiful region. There's so much
Yes.
going on there.
Actually, everybody should check out the image on Zenfolio as well. Brock, I think you have this one up on Zenfolio.
I do, yes, I've got it on Zenfolio. And I read somewhere that it's actually this star here is the one that's actually the star that's emitting a lot of ultraviolet light that's illuminating or causing the rest of the gases to glow.
Wow.
Or at least
Wonder-
it's somewhere up, somewhere in this area, and that's one of the brighter ones. It could actually be this one because that's kind of a reddish looking star now that I think about it. But I was reading up on it earlier. So.
Very cool. So Calvin, we'll post the link to the site before long. Tonight we'll do that.
Okay, great.
Okay, so we should move on to Dan. Dan, have you left for the Plaskett, or are you still around? Can you do your thing?
I'm still here, so
Oh, okay,
I'll
great.
go quick. David's already buried the lead, but I have to run across the parking lot and look sharp as I get the Plaskett up and running tonight. But I'm just going to share a couple images here, and then I'll get over to that, and you'll see me again in a little while. So what you're actually seeing tonight is going to be my imaging journey as an astrophotographer in reverse. I didn't come into this pursuit as a photographer, so I learned on very long focal length optics, and this here is actually about as wide field as I get. And this is using a 100mm lens. So in a second, we'll get into the longer, more complex type of imaging, but I thought it was nice to start with something like this because it's run and gun. And the background on how I got into all of this was a little bit funny to think about, which is that I was just listening to an astronomy lecture in school. I heard a description of how images of space are created. And I was young enough and brash enough to go, I could do that without knowing anything about cameras, without knowing anything about astrophotography, without knowing anything about the night sky. And what that led to was a decade of enjoyment and fun as I got to piece things together and create shots like this. So why I wanted to start here is that this is one of the more attainable images in terms of the kind of gear that you need to do it. It's using a DSLR or an equivalent that's modified. It's using a camera lens from a mass producer, and it's using a tracker that's not guided. And it's using a bunch of 30-second exposures right on your 30-second limit, David. The only secret to this one that was a little bit different than the usual was that the lens was a little bit chunky. So it was quite a large lens that allowed it to gather in quite a bit of light. But the other thing is that this was only 30 minutes. So this is my latest evolution, because I've realized as the working life takes over, sometimes you have to get something done in 30 minutes. And this is the way to do it. I think I lied. This is 48.5 minutes, and it was made out of 97 30-second exposures. So that's my first image for the evening. And here's the second. So this is a shot off the Plaskett. And this is actually more akin to where I started. I've been on and off as a Plaskett telescope operator for public programming like this since I think 2013 now. And this was a shot into what's called ARP 2, oh no, which ARP are you? It's NGC 3718, but I can't remember the ARP code, ARP 214. And so this is an interacting galaxy, and it actually shows one of the compromises for using a longer focal length setup, because there's a nice little galaxy off to the side of the screen here that I had to sacrifice to the cause, because if I had moved this a little bit less left, there would have been a nice big dust mote that destroyed the entire main galaxy. So I had to make a choice, and I chose to keep the pretty cat's eye instead, and wound up with this image. And this one is a neat one to show because it really goes to the credit of what the Plaskett is. If you look at these stars, they're sure a tiny bit elongated. The other image I showed you is 105 millimeters. This is 9.2 meters of focal length, and there are 3-minute subframes unguided, which means that it's a 100-plus-year-old gear that was tracking without anybody doing anything to coax it along the way, unguided at a 9-meter focal length. And you can barely keep a 105-millimeter lens working on consumer-grade stuff at 30 seconds. This is doing 3 minutes. And it came out with this kind of sharpness, clarity, and detail. And it was doing this from the city here in Victoria. And so just very quickly, one final thing, if you're wondering what my latest efforts have been, because there's been a lot of discussion tonight about light pollution and what you can do from downtown in the city. So this, I think this is more an exercise in madness than anything else, but is a shot of the Eagle Nebula that I took off of a condo balcony across 3 nights last week, which was about 9 hours of total exposure across the 3 filters. And this is again in the Hubble Palette. So right in the center, you have the pillars of creation. And again, using the techniques that have already been discussed this evening, you have ways of getting past light pollution that are quite unique and quite interesting, and allowed me to separate out not just the full moon for some of the frames, but also all the light pollution the city produces. And that's my Cliff Notes version of imaging, because as I said, I have to go do a mad dash across the parking lot. So thank you, everybody. And thanks for having me on the panel, David.
Thank you. Well, I surely think we have outstayed our welcome. So, but I sure hope everybody enjoyed the diversity of the group, and I am so pumped up by the whole group here in Victoria. There is so much talent here, and I really would encourage you to go to the Rastan Folio site that I just put up on the chat. We could probably put that up before we leave this evening as well. There was a question about where we like to photograph. I don't know if I could answer that really quickly, but there are a number of sites. We might have to leave that for another time, but check out dark sites. There's lots of websites that show dark sky areas or light polluted, lack of light pollution areas. And there's areas out along Tofino. There's even areas in Victoria where you can go where there isn't many city lights. So yeah, hopefully that should tide you over until we can talk about this another time. Anyways, thank you so much for everybody attending, and I hope you enjoyed the pictures.
Thanks so much, David, and to our entire panel. Fantastic. I'd heard bits and pieces about those techniques, but seeing the different things you have to think about in putting together one of these images and the cool technology that's come out in the past couple of years is fascinating. I don't think we have a lot of questions, nor do we have a ton of time to take questions, except for our Ask an Astronomer segment, which we're going to head off to right away.
Very good.
Yeah, we've got about 20 or so minutes for that. So I'm going to turn things over to Amy Archer to introduce our Ask an Astronomer panel. Hi, Amy.
Hi. So this is the fun part where everyone can interact a little bit for starters. So as you have probably been collecting questions as we've gone along, please put them into the chat window, either in YouTube or on Zoom if you're on Zoom. And then we will pass them along to, we have James DiFrancesco, who is the director up at the observatory. And we have Jonathan as well, who is a student at University of Victoria. All right. So hello and welcome to you both. And, so let's just get started. Is that all right?
Sure. Yeah, absolutely.
All right. First question, Jonathan, for you is what are you studying at UVic?
Physics and astronomy. I guess I didn't mention that.
No, that's okay. All right. So first question is about SpaceX. And James, this might be for you, but I'm not sure. So there's a bit of a rumor, I guess, that that SpaceX is going to be doing some sort of advertising in conjunction with a Canadian company. And they're going to project back to Earth. What is that exactly going to do for our viewing, and how do we stop it?
Fortunately, it sounds a lot worse than it is.
Okay.
Based on my understanding of it, they're going to launch a satellite that has basically an LCD screen on it, or a screen on it of some sort, with a live video feed of that screen. And then they're going to sell space on that screen for advertisements. So I don't think we'd be able to see it from the ground, so it hopefully won't have any adverse effects on what we can see in the night sky. It's still a bit of a silly thing, though, if you ask me.
Yeah.
Having advertisements in space.
Okay, so there is a lot going on in orbit these days. In the last couple of years, we've seen a real explosion in terms of the numbers of satellites that have entered orbit. And largely these satellites are so-called mega constellations that are intended to provide internet access to across the globe. It's a very interesting idea. And of course, it'll be great to be able to check your Facebook page from the North Pole. But unfortunately, it has a downside in that all of these satellites will have an impact on the night sky in that we will have many more instances of satellites passing wherever you're looking. And there could be tens of thousands of these satellites up there in a relatively short time. SpaceX is just one company that's putting these satellites up into orbit, but there are several others out there. So I guess this news about the Canadian company that is partnering with SpaceX, I suppose, to put this advertising in space is, I guess, not surprising in that environment where now we're getting a really, really big exploitation of space by commercial enterprises. Exactly how we manage this is still to be seen. There isn't a lot of regulation out there. So in a sense, it is a threat to what one might call the sanctity of the night sky, because our ability to enjoy it without something passing in front of us while we're doing that will be challenged. But from an astronomical perspective, it's almost worse, because these satellites can occasionally wander within the field of view of the telescopes that we're pointing at to try to image into deep space, and affect the image dramatically, like even ruin the observation. And I mean, it sounds like, what are the chances of that happening? Well, it's surprising that we actually do get a fair number of satellite passages already. But there are new observatories out there that are hoping to map the sky in very wide fields, and they will definitely be impacted by these satellites. So what to do? Hopefully there will be greater regulation of these, and I know that many of these companies are working with, well, at least SpaceX is working with astronomers to try to come up with ways to minimize the impact on the night sky by, for example, having low reflection coatings that will minimize the amount of light reflected from the sun down into onto the ground. So I think that there's lots to be done, and hopefully we can come up with a harmonious way to share the night sky with these companies.
Lovely. Thank you. So next question comes from YouTube. And the question is, I realize astronomical time is long, but the Horsehead Nebula doesn't seem to have changed much in 50 years. Shouldn't there be some visible change? If not, when will we see the change?
I can answer that. Actually, I think there is an observation of the Horsehead Nebula changing on human timescales. I'm afraid I don't have that at my fingertips, but I do recall seeing an observation where they blinked between two images and showed very slight changes in the Horsehead over a number of years. I mean, yes, these things do take thousands of years to change, but even little bits can be noticed in short amounts of time, like several years or so. So I would Google blinking Horsehead Nebula or something like that, and to see what that change was how that appeared. But I do think you can see some very subtle changes in even a short amount of time.
Can I jump in on that one?
Sure.
Yeah. So there's so the Horsehead Nebula, I think one reason it's harder to see some changes on it is just because it's so large. Like the scale of things in the Orion cloud there are on the order of like tens of light years or so. So even if things are changing very rapidly, like they would appear very, very small against the rest of the nebula. One example where you can see some fairly dramatic change over human timescales is with the Crab Nebula. So that's a supernova that happened about 1,000 years ago, and its supernova remnant nebula is only about 2 light years across, and it's expanding out at on the order of 1,000 kilometers per second. So over even the 20 to 50 years that we've been taking good pictures of it, you can actually see like some quite noticeable changes. So if you Google a Crab Nebula time lapse, that's a really good one to see things changing on an astronomical space scale, but a human time scale.
There are plenty of other things in the night sky that, although 50 years isn't a very long time in astronomical terms, there are many things that we can see evolving over that period of time. I believe planetary nebulae are one of those things. They sort of expand as time goes on. We can watch the orbits of planets and exoplanets, which is on the scale of years usually. So most things in space you see don't change very much at all over the course of the human lifetime, but some things do.
Right, thank you. Next question is there any news about when James Webb will be up and running?
Okay, so the latest that I've heard is, well, okay, I think the official launch date is still the 31st of October of this year. And right now, many of the components are being sent to French Guiana, where the telescope will be launched on a European Space Agency Ariane 5 rocket. Now, I've also heard that because of some issues with that Ariane 5 rocket that have come to light, the launch may be delayed a little bit, maybe into November. But as far as I've heard, I don't believe that's been official yet. But that is a relatively minor delay after the many, many delays that this telescope has had over the decades. So a little waiting 2 more weeks or so isn't too bad, especially if we have greater confidence that the rocket is going to work as planned. So yes, hopefully we'll start getting some nice James Webb images, perhaps as early as Christmas. And maybe soon thereafter, as the telescope is sent out to its location in the where it's supposed to be, which is not orbiting the Earth like the Hubble Space Telescope, but at a location called the L2 point, or the Lagrangian point, in the Sun-Earth system, which is a little point of dynamical stability in the line between the Earth and the Sun, and well, the Sun, the Earth, and this point. So, and it's put there because, in part, because it will be able to observe without having the Sun and the Earth in the sky at any given time. They can always look away from both things at the same time and shield the telescope from the light from both of those objects at the same time.
Right. Thank you. So a question from a younger viewer,
Okay.
which is, why, when you get to space, why is it so cold when the sun is still so close?
It's a good question.
It is, although it's, if I were to take a stab at that question, I would say that the way we measure temperature on Earth is rather different to the way we measure it in space. Because on Earth, we have an atmosphere around us that can transfer heat to us through conduction and convection. Whereas in space, all thermal energy is transmitted through radiation because it's a vacuum and there's no medium for the heat to travel through. It has to travel via light. So if you go into space with a thermometer, what you would find is that it would read whatever temperature it was before you took it into space. And if it's in the shade, it would slowly drop in temperature. But if it's in direct sunlight, it would probably rise in temperature depending on how far away you are from the sun. So it's one of those situations where you have to sort of take your intuition and modify it to fully understand the situation that is going on in space.
Right. Thank you. Next question is what sorts of things, so we did learn earlier this season about the new building on the hill, but there's many other things that are done on the hill, right? So what are the types of, I guess, professions, if somebody were getting into astrophysics or not, what kinds of jobs are done on the hill?
Okay, I'll take that answer. So up the hill, it's what we call a campus of the Hertzberg Astronomy and Astrophysics Research Center. And so that encompasses a lot of different astronomical activities, that not just those that are connected with the Plaskett telescope and the 1.2 meter telescope that are also on the summit of the hill. So the Hertzberg Research Center is sort of like Canada's national laboratory for observational astronomy. And what we do is that we try to provide support for Canada's astronomical community to enable Canadians to use the best research telescopes that are available and use them well. And by using them well, that means not only do we manage the access to these telescopes in Hawaii and Chile and soon other places, but also we provide the instruments for which these telescopes use to make these very sensitive observations of the deep universe. In addition, we work with the astronomers that at Canada's universities to make their programs as efficient as possible. And on top of that, we store the data from those telescopes, allowing Canada's astronomers to download them, and then also providing some computing resources for them as well. So that work encompasses a whole bunch of various jobs. You have research astronomers such as myself who have gone and begun a career in astronomical research. And we use the knowledge that we have acquired by observing with these telescopes to make the best advice, to give the best advice to other users of those telescopes. And then we have also people who are engineers, machinists, and so forth, who are building the hardware that these telescopes use, for, these cameras and spectrographs, the instruments on these telescopes. And on top of that, we also have people who are very well versed in data management and archive support, computers, if you will, that handle the data side of things. And so, yeah, we're a very active and dynamic research center that have quite a surprising variety of professions going on the Hill.
Thank you. We're starting to come to a close, and so I have a couple more questions.
Sure.
First is for each of you to answer. What is your favorite constellation? And why would be a good addition, but just like...
Okay, sure. Shall I go ahead first?
Sure, if you like.
Okay, so my favorite constellation is probably the Perseus constellation, which is sort of an odd choice because it's not a very bright constellation, but it's one in the northern sky. But I like it so much because it contains a molecular cloud, which I have spent years studying to understand how stars are forming within that cloud. So Perseus, the Perseus molecular cloud is about 1,000 light years from the Earth. And it is, I think, about 10,000 times the mass of the sun, maybe 100 times. 1,000 times the mass of the sun. And parts of it have been forming stars for tens of thousands of years. And so we see these young stars as they are borning out of this dense gas in this cloud. And I have spent many years studying different parts of that cloud to try to unlock the secrets of how stars form out of such huge amounts of gas and dust in the galaxy. So Perseus. It's also the name of a winery out in the Okanagan too, so that doesn't hurt.
My favorite constellation would probably be Orion, which is a common choice, but basically the reason behind that, I would say, is because it and the Big Dipper were the two sort of constellations that I was able to recognize first when I was young. So that kind of stuck with me as well. And it's got the Orion Nebula in it, which is basically the first thing that any astrophotographer would try to image when they get into deep sky imaging. My second favorite constellation would probably be Sagittarius, because it's also got very many beautiful deep sky targets to image in as well.
I'm going to squeeze another question in. Sorry, David. So the question is about Voyager 1 and 2. Okay. And it is, how did they make it through the Kuiper Belt and the a cloud without hitting anything?
Okay, so I'll answer that one. So Voyager 1 and 2 were space probes that were launched from the Earth, I think around 1977. And in the intervening decades, they have passed the major planets in the outer solar system and are now proceeding out of the solar system and have reached more or less a part of the solar system called the heliopause, where the wind of particles streaming off the sun is now indistinguishable from the streams of particles from other stars in the galaxy. So they're at a point where they actually appear to be arguably leaving the solar system. So out in that part of the solar system, there's this thing called the Kuiper Belt, which is this collection of millions of small icy blocks that are left over from the formation of the solar system, Pluto being perhaps the largest and most well-known of them. And then beyond that, there's this very large cloud called the Oort cloud, which also contains lots of icy blocks. The Kuiper Belt probably formed out of the disk from out of which the solar system itself formed, and then the Oort cloud is just this remnant cloud of icy blocks that are left over and scattered in all directions from the sun. So why is our Voyager 1 and 2 going to hit any of these things? Probably not, because even though both of these, this belt and this cloud, contains billions of these icy blocks out there, they're so far spread apart that it's very unlikely statistically that Voyager 1 or 2 will hit something of that magnitude as it proceeds out of the solar system. I mean, you can never say never, but I think that it's just unlikely that it's going to happen. I mean, we call these things clouds, but they are still extremely diffuse and low density. And so it would be very remarkable if it would be hit by something on the way out of the solar system.
So where are Voyager 1 and 2 located now? Like how?
They are, I think, about 50 times the distance between the Earth and the sun. I can quickly look this up.
Jonathan, or are you there, James?
Yeah, I'm here. So it is presently 11 billion miles from the Earth. Wow. So it is one of the most distant things that we have ever sent out into the universe so far.
The most, actually.
I wasn't sure if Pioneer 10 or 11 have beat it or not, so that's why I was hedging my bet.
Yeah. The Voyagers were launched at a much higher velocity, so they overtook the Pioneer craft.
Okay.
And in fact, an interesting fact about the Voyager probes is that Voyager 2 was actually launched before Voyager 1. But Voyager 1 was launched at a higher velocity, so it overtook it eventually.
Interesting. Was that Aaron? Yeah.
Sorry, go ahead.
I was going to ask one last question. Are you? Yeah. Okay. So, which is just, are you able to tell us, Jonathan, maybe if you want to start, how did you go about getting into where you are in terms of studying astronomy or physics and yeah?
It's a good question, although I'm not sure if I have an interesting answer to it. It's just something that has always interested me when I was young, and when it came time for me to decide what I wanted to study at university, I sort of chose to go down the physics astronomy type route.
And then James, same question for you. How did you, I guess, make the decision to go into your field, and how did you get there? How did you get to where what you're doing now?
Okay, so let me just say that I did a quick peek at a NASA page, and Voyager 2 is actually at 127.25 times the distance between the Earth and the Sun, and Voyager 1 is 153 times that distance. So I was off by a bit. So just to be accurate, that's how far away those dudes are. And amazingly, they've been going for over almost, well, like 44 years. Goodness, I'm old. So yeah, they're just going, and they keep going. They're like the Energizer bunnies of space probes. It's amazing. Okay, so the question is about me. How did I decide to become an astronomer, and how did I do it? Okay, well, that's a very interesting question. So I think the way that I decided to become an astronomer was that I had an abiding interest in the universe as a kid. I read a lot of books and so forth, and I was interested in it. But I think what actually triggered me to become think of an astronomy as a career was, interestingly, when I found out that stars have names, because I was kind of blown away by the fact that someone had actually gone ahead and named all of these stars, and you could actually identify them by name in the sky. And I know that sounds kind of silly in retrospect, but it occurred to me that stars were so interesting and different that they went ahead and named them one after another. And that triggered my curiosity about astronomy a little bit more, about what stars were and how they were different from each other. And I do remember in high school, trying to figure out what I wanted to do with my life. And I remember looking up at the night sky, and I thought, maybe I'll try to become an astronomer. So I had already started reading books about it, so it wasn't that crazy. But I mean, I didn't know any astronomers, and I didn't know what to do. So talking to some people, I started taking classes in math and in physics and chemistry and so forth. And that allowed me to prepare to have astronomy and physics and math classes at university. In my case, I went to the University of Toronto. But to become a research astronomer, you have to more or less get an advanced degree. So you have to go to graduate school to earn your master's or your PhD. And that means another 4 to 6 years after your undergraduate degree. And though it's a different kind of studying than what you do as an undergraduate, because you take fewer classes, but you also are engaged in learning the craft of becoming a research astronomer, where you are mentored by someone, your supervisor, and you learn what you have to do to to isolate a problem, figure out how you need to approach it, how to acquire the data, how to analyze and interpret the data, and how to write up those results. And that's a different set of skills than the sheer background that you learn as an undergraduate. So, so I got my degree at my PhD at the University of Texas at Austin, in Austin, Texas, which, and then after that, I did a couple of postdoctoral appointments at a couple of locations in the United States. That's a few years here, a few years there, sort of like the journeyman experience from medieval times, where people who were apprenticed would then go off and study with other masters before becoming masters themselves. And eventually I got a job here in Victoria because I had acquired a set of skills in observing in a particular way that was considered of interest and valuable, fortunately for me. And so I was lucky enough to be able to be hired here at the Hertzberg Research Center in Victoria, way back in the end of 2001, and I moved here in June of 2002.
Wonderful. Thank you both for being on the panel tonight. Your answers were wonderful. And as always, my last question goes to David Lee, which is, can you tell us a little bit about EAA?
Yeah, it's unfortunate. I thought with my discussions with Dan that we might be able to see some streaming tonight from the Plaskett, but it looks like the wind has got the better of us, I guess, and we can't open the dome. So there are always sort of safety concerns in terms of opening the dome, and it doesn't appear that it's safe. So as always, we're always prepared. I kind of laugh because EAA is meant to be about streaming, and I think of all the shows we've done this summer, we may have done it only once or twice. So we've always been sort of prepared with some dialogue beyond that. And tonight, I think we decided that we're going to do a little bit more of a deep dive into narrowband imaging. So we're going to probably have a little bit of a chat about that. I'm sure the folks here have some images that we can sort of take apart. And I believe Jonathan has prepared some information about what narrowband imaging is about.
That's right.
So Jonathan, take it over.
All right, thank you. So yeah, we've seen a few examples of narrowband imaging tonight in the previous sections, but I guess I wanted to dive a little bit deeper into why we do it and what type of information we can gather from the cosmos by taking the light that we get and separating it into different wavelengths. As amateurs, the amateur astrophotographers, the chief way we utilize this technique is by isolating different materials that nebulae or whatever are made out of and assigning them to different colors in our images to show the structure of these objects. So the structure of objects is one piece of information that we can glean from this technique. But it's not the only one. There's also various techniques that we can do if we have precise isolated data on different wavelengths to determine things such as the velocity of objects, their distance, their age, their exoplanet detection techniques that rely on narrowband imaging to see how different spectral lines are shifting over time. So there's really a lot of information that astronomers have been able to pull out of just light. And that's really out of necessity because astronomy is probably the most visual of all fields of science. Up until very recently, all the information that we receive from space has to come to us in the form of light. We can't, well, we sort of can now, but we can't really go out into space and take a piece of it and bring it back with us to a lab. We can't really access the things that we're studying in traditional ways. So we have to find clever ways of taking the information that we have access to and pulling as much information out of it as we can. And for most of astronomy history, that's just been light. Light is the only thing that travels across the universe that we can detect up until recently, because with the discovery of neutrinos, I think that was in the 30s or something like that, we can detect neutrinos coming from space, and neutrinos are subatomic particles. And since 2015, I believe it was, we can also detect gravitational waves. So if very large black holes or neutron stars or what have you are interacting with each other and colliding, they radiate energy from that interaction in the form of gravitational waves, which we can collect. And we can sort of see things in space with light, neutrinos, and gravitational waves, and not much else beyond that. So we have to be very creative with how we utilize the information that we have.
Great. I guess with the narrowband imaging that we were talking about this evening, I guess as amateurs, we could utilize those filters. And in fact, I guess the traditional narrowband set would be H alpha, oxygen 3, and S2. So by using those filters, I think we saw some examples tonight where those filters were mapped to particular colors, like say the Hubble Palette, to show structure in our imagery. So yeah, that's quite fascinating. And the other thing that I had high hopes for, living in a very light polluted area in my neighborhood, I was looking forward to using narrowband filters along with light pollution filters to sort of attenuate the light of the artificial light, and also even to image during full moon as well, because the majority of deep sky imaging is typically done on moonless nights to really take advantage of the signal.
Yes, that's right. Narrowband filters are an absolute game changer when it comes to combating light pollution.
Yeah. Actually, I know there's quite a number of people here, like David and Brock and Dan, that use these filters. And there's the traditional set that I mentioned. And actually, for those of you who are using digital SLRs, there's this new type of filter called dual and triband, which allows people with one-shot color, like digital SLRs or one-shot color CMOS cameras, to actually not have to take individual shots, which means numerous shots. So if you have a one-shot camera, then you would only take this one filter, which could be like a dual or a triband, and basically get the effect of having integrated mono images through each of those filters. So I think, I mean, I have just purchased one. I have not actually used it yet, but I don't know. Dan, are you still on the line?
Yeah, just briefly. So apologies, everybody. The wind did kick up here, which knocked us over the basket. Those filters are quite useful for the one-shot color world. I started using one probably last summer now, I think, David. And they still require the same amount of time from you in total. You still, if you needed 10 hours with a monochrome camera, you still need 10 hours with a one-shot color camera. But you're able to get past the big detractor of a Bayard sensor. So normal color sensors have what's called a Bayer matrix. It goes red, green, green, blue in front of them. What that means is that if hydrogen and sulfur are both in the red, you're only using about a quarter of that sensor at a time if you're taking an image through one of those dedicated filters. What these new dual band and tri-band filters allow you to do is to shoot oxygen on your blue and green pixels while shooting sulfur or hydrogen on your red pixels.
So you can better utilize the sensor.
Yeah, you don't waste 3/4 of your imaging area on doing nothing. So it actually gets past one of those big challenges that one-shot color cameras have had. And it's not perfect, but it's been the biggest detractor for them really going toe-to-toe in the narrowband world with a monochrome camera. And now they're much better able to do so. There's still some little blips in there, like the dyes on the Bayer matrix aren't perfect, so you get bleed across the different spectrums of light through the different filters in the Bayer, but it's pretty close. I don't even have a great one, and it's been exceptional.
Yeah, I guess this is a nice compromise, because I mean, the alternative is to use a mono camera and do separate shots through individual narrowband filters. Yeah, which isn't necessarily that palatable to people. Just means more exposures, right?
Well, to give you an idea, I think I flashed up very briefly an image of a narrowband shot, and my refractor is nice, but it's not perfect. So with narrowband, it really shows that there's a little bit of focus change between your different wavelengths of light when you're using these very fine narrow filters. Mm-hmm. So when I shot that picture, I shot one filter per night for 3 nights. There was no point in me trying to rotate across filters because I wanted to be sleeping. And so I had to make a choice, and my choice was to wake up and go to work the next morning. So in that sense, there were some limitations. If I'd been using one of these dual or tri-band filters, you could take that picture in one night and then get 3 nights worth of data if you wanted to. So, but I think that's my last comment for the evening. So I'll also say goodbye to everybody.
Well, thank you for participating tonight too.
Yeah, thanks for having me.
So David Payne, I know that you have used narrowband now. Have you done that on one shot or on mono?
I have done a little bit of both.
Okay.
To strictly use narrowband on one-shot camera, you're going to have to separate the channels,
right?
And when you do separate the channels, you do lose your resolution, because you're now and you're cutting back the area that's involved. So one way or another, you have to pay the piper.
Yeah, so normally narrowband imaging is done with a mono sensor, not with a color.
Yeah. Where it can be useful is if you're taking say a picture of a galaxy, and a galaxy typically has areas of hydrogen nebulosity embedded in its spiral arms. So it would be very interesting to take your standard one-shot color pictures of the galaxy, also take it with your filter on, and then put those images together, and you'll really get those areas of nebulosity to stand out more in a galaxy image. If you're doing a nebula, well, one of the nice things that the narrowband filters do is they make the the stars smaller, because they're taking a smaller fraction of the light from a star, which is emitting across the spectrum, and you're only taking a bit of that. But when it comes to the nebulosity, you're taking most of the light that's being emitted from the nebulosity. So it makes the nebulosity brighter and the stars dimmer.
So Dave, I think one of the downsides I've heard is it messes up the star color.
Yes. And if you enjoy taking narrowband, if you enjoy taking narrowband images, which a lot of us do, you kind of say, I know the star color is wrong. So what?
It goes with the territory. Yeah.
Or you can spend time in processing. And one of the things you can do with narrowband is try and blend sulfur and oxygen and hydrogen in different proportions and assign those as sort of a false RGB, which is I've done it sometimes, and you get more or less the right star color, but you do pay for it in the structure of nebulosity. Isn't as stark. It becomes a little bit blended, and your colors tend to be a little bit blah in the nebula itself. It's all, what are you trying to convey? What are you trying to find out from the picture? Are you doing it for aesthetic reasons? You'll end up with a very different picture than if you're trying to use it to learn or understand what's going on, right?
Yeah, there's definitely two different levels. And I hope people got that sense this evening. I mean, there's certainly narrowband just for the pure aesthetics, but there's an absolute science to narrowband as well. Like if you want to learn certain things about what you're viewing, you will utilize those wavelengths to do that. Now, Dave, you've often commented to me that your narrowband filters make you think about, I guess, flow. Like as an engineer that did that, what sort of things are you seeing in these images? Like when you do narrowband, you mentioned that you see certain characteristics in the image.
Well, I'm used to physics taking place at our sort of normal day-to-day scale
on the Earth, right?
Right. So
yeah.
So what causes fluids to flow on Earth is pressure. Gas molecules bump into each other often enough. We usually have the effects of gravity, but we're not really looking at the effects of photons hitting our materials or anything like that. So there's certain things that occur that causes mixtures to separate. And we take advantage of that in processes, industrial processes, and all sorts of things, in baking, in all sorts of things that cause materials to separate from one another. And usually it's the expenditure of energy is required to cause that separation. So when you say you've got, say, a supernova explodes, and we photograph the nebulosity that results from that, and we see that oxygen might be in a different spot. There might be a cloud of oxygen, but it's not in the same spot as a cloud of hydrogen. Now, I know it's all in proportions, but there is a spontaneous separation that's going on there between these elements that were emitted during that explosion.
So is that normal on Earth with materials, that they would stratify in some fashion? Or
well, sure, like you're mixing oil and water will separate.
All right, okay, that's an obvious one, right?
But so it gets me to thinking, so what do you've got ions, you've got molecules or something, they're all getting bombarded by the photons from a star that's causing them to move. So, and I've also read about, well, how we might get very distant spacecraft or send things into deep space now is to create a sail on them, shoot a laser at them or shoot photons at them, and the momentum or the energy of those photons hitting them will cause this spaceship to move away from us, right? So are these molecules of hydrogen and molecules of oxygen acting as these sails? They've got a certain mass, so being hit by a photon will impart a different amount of momentum to them, so they might have different amounts of momentum. They might have different cross-sectional areas for a photon to hit. So one might be hit by more than one photon. And is this behind the creation of these separations of these gases that we see? Now, I might be talking off, and I know I'm talking off the top of my head.
So, Jonathan, is it reasonable to relate things that we see on Earth to things we see in space, or is a scale a factor in this?
It really depends on a case-by-case basis, because on the one hand, if we couldn't compare anything in space to anything on Earth, then we can't know anything about space at all.
Oh yeah, that's a good point.
Yeah, we have to extrapolate the physical laws that we experimentally observe on Earth to the cosmos. Otherwise, we have no way of understanding it apart from going there. And you can't really go there unless you know that once you get there, physics is going to work the same way as it does on Earth.
Yes, that's an assumption that we make.
So it is. So unfortunately, it seems to be a good one.
So all the fields of science, whether it's astronomy or maybe the possible exception of quantum physics, they're all based on, at a base level, on an energy balance and a mass balance, right? Or a mass energy balance.
I suppose so, yeah.
Right?
Yeah.
I mean, when I look at the nebulosity, I'm so used to looking at shock fronts, viscous fingering, and when I say look at, I mean indirectly measure, because I can't actually physically see what's going on underground in aquifer, in a CO2 storage project, or in a water flood to produce oil. You get shock fronts, you get this, it's caused by viscosity, you get fingering of one material through another, you get gravity separation of materials. You know, the actual mechanism is quite a bit different, but the effects you see are very analogous.
Mm-hmm.
The nice thing about looking at the nebula is I know it's only light that we're actually getting, but you know, when you're talking about what's happening underground, it's actually the opposite. You never actually see what's going on with your eyes. You can only indirectly measure things. But you have point sources in space, which are stars. You have point sources underground, which are wells, right? You've got, and when you go to modeling, the modeling is very much the same. What's going on in one going on in the other.
Maybe that even though we're dealing with different physical processes in these two scenarios, it could be that they follow similar rules of mathematics. They're governed by similar equations.
Exactly.
They produce similar results.
You've got the diffusivity equation, right? It's basically the same.
Or like the inverse square law. We've got sound following that principle, and so does gravity. And so does light.
Well, you know, geophysics, which is shooting sound in the ground so that we can see underground, is in some ways it's because you've got shear waves and compressive waves. It's very analogous to being able to shoot photons through glass and different materials. You'll get some reflection and some passing through, right?
Mm-hmm.
Actually, I just see Brock looking at his screen. Brock, are you actually seeing some clear skies?
No.
No. No. I was hoping for maybe 3 times EAA this season.
It was getting pretty cloudy. I didn't set up.
Okay, fair enough. So what do you think about narrowband? I guess you're trying to do that yourself.
Me?
Yes.
Well, I had a brief, well, it wasn't that brief, couple months of using some narrowband equipment. It was a lot of fun. I bought a one-shot color camera and waiting for a filter to arrive. But supply chains are a bit tight, but I enjoyed it. It was really interesting. It's a lot more work, but
Yeah.
But I did find the filters focus was different for each filter quite regularly. So, you know,
Actually, I often wonder when people view the images whether they understand how much work has been involved.
I doubt they do unless they.
I doubt. Yeah, you're right. You're right. Yeah. Yeah, because I think when I mention special processing, I don't really give people a feel for how much effort it actually is. I don't know, maybe it's not necessary to know, but I guess for those of us who spend all that time collecting data and go through the process of going through all the different types of processing and rolling it back and moving it forward and rolling it back and moving it forward. I mean, these permutations can drive you crazy.
Yeah. Although once you've done it a few times, I found I get into a groove, and you know, as long as the data is good, and the narrowband helps you get good data. So in that way, the narrowband actually made it easier, because with just a one-shot color, you're just like, okay, look at this gradient. How the hell am I going to get rid of that? You know, and whereas the narrowband often is much cleaner. And you just
I did mention the fact that
you stack it and you know,
I mean, it's quite effective in terms of minimizing or eliminating light pollution and even moonlight, right?
Yeah.
You got more time, as I say. Most of the time you kind of have to wait for dark skies, but I guess with narrowband you shoot anytime you want.
Within limitations.
Yeah, I did a couple really good shots. I don't remember which they were, but I got some really good images just in almost complete full moon. And that was kind of nice.
But you have to have clear skies. That's
yes.
That's the thing. That's the problem that we have here in Victoria, for sure.
Yeah, unless it's April 1st and you're an OPT.
Yeah. Well, everybody looks kind of tired. I don't know. We don't have to go right to the end. I think everybody had a good insight into imaging tonight, or astrophotography tonight. I enjoyed listening to all you guys. Like I kind of think I know your stories, and then I always hear something additional every time I hear you guys speak. So I like that. And I was just telling Dave the other night when we were on Zoom that certainly the imaging groups at the star parties this season have been the highlight of my summer, because I get to really hear all the stories. Like, even though I might not be able to do them, I can hear the stories behind the pictures. So thank you.
You're welcome.
All right. Yeah. Thanks, everyone. David Lee and the whole panel. And thanks to Amy Archer and James DeFrancesco and Jonathan for doing the Ask an Astronomer. Those were actually a lot of interesting questions. Thanks to all the members that joined us on the Zoom call and all the viewers on YouTube. This was actually a lot of fun to see a wide array of photographs and to see how they're explained. The rigor that you go through just to capture them is wonderful. I guess the only thing I need to add is that the next Saturday night star party will be on September 11th. So people can go to our website, centeroftheuniverse.org, to follow that and get all the info for that. Okay, I think that does it. So good night, everybody.
Yep, good night.
Good night.